Welcome back. This is a critically damped RLC circuit. Capacitor, inductor, resistor, voltage across all three of these guys, current through all three of these guys. Node A, this is a 10 microfarad, this is a 0.4 Henry. This is our initial current through the inductor. This is our initial voltage across the capacitor. R is unknown. We are given that this thing is critically damped. So we know what math to use, the critically damped toolkit. We're also given the initial energy in these guys, 12.5 millijoules in the inductor, and the initial energy in the capacitor at 0 is also 12.5 millijoules. So from that, we're going to get our I and our V, our initial I and our initial V. Okay, we're asked to find part A, R. We're asked to find the initial voltage and the initial current. We're asked to find our D's. We're asked to find I as a function of, or I sub R as a function of time. So for all of these RLC, there's certain tricks, and there's KCL, which is what? It's I sub C plus I sub L plus I sub R equals 0, and you can solve this for, whatever you want. And the other one is this I equals C V prime, I in a cap, right? But the voltage, it's the voltage in the cap. You could put a C there, but I mean, all three of these elements have the same voltage in there. So specifying a particular element would be redundant for the voltage, but you could. And then we've got the V equals IR, I sub R, R. Ohm's law, current voltage for a cap, KCL. These are our tricks that we use over and over again in these RLC problems. So part A, so this is critically damped. It's given that. So the condition for critically damped is that alpha squared equals omega 0 squared. That's the condition. And we have these formulas. We have alpha is 1 over 2 RC, and omega 0 is 1 over root LC. So plug these into here, and you get 1 over 2 RC squared. It's alpha squared equals 1 over root LC squared. So okay, just realizing the condition for critically damped is this, and then plugging in these two formulas into that, you get this. We can use this thing here to solve for R. The only unknown is R. We're given C, we're given L. So unsquare both sides. So 1 over 2 RC is 1 over root LC, and we don't know R, but we know L and C. So 1 over root L is 0.4 henries, and C is 10 times 10 to the minus 6, 10 microfarad. That works out to 500. Just plugging in the values of L and C here. So this is alpha. So we need that for later. going to put a little box around it like that. We need this later. All right. So we can go back. We can go back to, you know, the extremes here on either side of the equation here and solve for r. So r is going to be just swapping alpha and r. It's going to be 1 over 2 alpha c, 10 times 10 to the minus 6. So it's going to be 100 ohms. First answer. Right? Just playing with these formulas that we're given and realizing that this is the condition for critically damped. And then it's just a little algebra puzzle. All right, then part B, we're going to use our omega sub-zero, you know, energy formulas. And so the energy in the initial cap is 12.5 microjoules. And that's using our formula. We're using W equals 1/2 CV squared, you know, for a cap, W in a cap. So is 1/2 C. There's our capacitance, and then V, the initial voltage squared. So yeah, just solving this for V0. V0 is going to be 50 volts. Likewise, the energy in the inductor is also 12.5 times 10 to the minus 3. That's just a coincidence that these are the same value. It doesn't mean anything. It's 1/2. The inductance is 0.4 and I0 squared. So I0 turns out to be 250 milliamps. Okay, that's part B and part C. All right, I'm going to use another piece of paper because this part of the solution is a little bit longish. So part D, we're trying to find D1 and D2. D1 and D2. These are the letters that are used. D's are used for a critically damped situation. And we have these toolkit equations, I call them. We're given V of 0 is D2 and V prime at 0 is D1 minus alpha D2. This is our, you know, this comes from our toolkit, right? But V0, we just solved for that, it's 50. So this is 50. So basically we know D2 already. We know alpha. Alpha was 500. We figured that out already. We know D2. If we had V prime at 0, we would have the only unknown would be D1, and we could solve for D1. So we need V prime at 0 and to solve for D1. All right, so if I had, okay, so then, you know, I need V prime at 0, so I need IC at 0 to get V prime at 0 via I equals C V prime. Right? If I had I at 0, I already have C, I could get V prime, and then I could plug that back into here. So we'll use KCL at node A, and that should give us I sub C, because we know. Let's write it out, see what happens. So I sub C at 0 is minus I sub L at 0 minus I sub R at 0. That's just KCL solved for I sub C. So these two terms are negative. And we, this thing we have, this is big I sub 0. So this is just minus 250. And this, we'll just use I equals V over R, I sub R equals V over R for this thing. So this is V, the initial voltage 50 over R, where the heck is R, 100. Okay, so yeah, so this works out to be minus 750 milliamps. Then backing up, we can use I sub C equals CV prime now. So V prime at 0 is going to be I sub C at 0 over C. That's just this I equals CV prime thing. And plug in this 750 we just solved for and the capacitance that we know. And this ends up being minus 75,000, and it has units volts per second. Then let's take this guy here and scoot him on down to here, and I'm just going to rewrite V prime at 0 is D1 minus alpha D2. So so D1 equals D1 equals D1 equals V prime at 0 plus alpha D2. It equals minus 75,000 plus, alpha's 500, right? 500, D2 is, what the heck is, where's D2? Where'd D2 go? It's up here. Times 50, it's gonna be, so D1 is gonna be minus 50,000 volts seconds. And yeah, this is D1. So we can, back to our toolkit, EQ, the general solution for V of t is D1 t e to the minus alpha t plus D2 e to the minus alpha t. And we know all of these dudes, so Vt is 50 e to the minus 500 t. That's D2 is 50. And then D1, just flipping these around so that you get plus on this side, minus term on this side. So it looks pretty, that's all. 50,000 t e to the minus 500 t, just, yeah. So that's our, that's just, they're not asking for that as a solution, but it's, you know, it's a handy dandy little doohickey we need there. So, you know, it's good to graph this stuff, right? So this thing here, I'm just going to graph V of t, and I of t is going to have the same format, which the next problem talks about that a little bit more detail. But I'm sorry, V of t, it's at 0. It's going to be this will be 1, and this will be t will be 0 here, so this will be 0. So it's just going to be 50. Now this is a line, minus 50,000 t is a line with a very steep slope. It's pulling it way down. And this guy is just a decay. This first term is just a decay. The second guy is a straight line pulling it down, but then the E part is going to start to pull it up. So it's going to dip some and then come to 0. This one happens to pass the axis. Now you don't really know that from looking at the number values. I graphed it, and I think I used Excel. But anyway, it's not surprising that it has this curve. The actual shape is some bit of guesswork. You should probably graph these numerically, right? Use a computer tool of some kind to graph these numerically, and then transfer those graphs to your homework. But I is going to have the same format. Now, that's important to point out now. Same general shape, because the next problem we're going to talk about that, how all of these signals, V of t, I of r, I sub r of t, I sub l of t, I sub c of t, they're all going to have the same shape. They're only going to differ in the values of the coefficients. These d terms are going to have different values. In fact, what are they asking for? We haven't even finished this yet. They're asking for I sub r of t. This is part E. What is I sub r of t? And just use Ohm's law, okay? Ohm's law, V equals IR. So I sub r of t is going to be V of t over r. Just divide this guy up here, divide it through by r, which is 100. You're going to get 0.5 e to the minus 500. So that's what this value is, 0.5, okay? Minus 500 t to the minus 500 t amps. That's our answer. Okay, and it's going to have this shape here. They all have the same shape. And that's what the next problem talks about. So that's a fun little problem. Thanks.